Hello, my name is Enes Kahraman and I'm a freshman at Bilkent University studying electrical and electronics engineering. And in this video, I'm going to briefly explain my Physics 102 experiment on resonance in a series RLC circuit. I'll talk about the aim of the experiment, the setup and procedure, what I calculated from the data, and finally the main sources of error. The main goal of this experiment is to study resonance in an AC circuit that contains a resistor, an inductor, and a capacitor connected in series. In an AC circuit, the inductor and capacitor each have a kind of opposition to a current called reactance. The inductive reactance is calculated by multiplying omega with the inductance, and the capacitive reactance is calculated by 1 over omega times the capacitance, where omega is 2 pi f, where f is the frequency of the function generator. At a special frequency called the resonant frequency, these two reactances cancel each other, so the inductive reactance becomes equal to the capacitive reactance. At this point, the circuit behaves like a pure resistor, the impedance is minimum and the current is maximum. The formula for resonant frequency is 1 over 2 pi square root of LC. In my experiment, I wanted to measure how the current changes with frequency, find this resonant frequency from the data, and compare it with theoretical value. The original lab setup uses a function generator to provide a sinusoidal voltage, a resistor, inductor, and capacitor connected in series, an oscilloscope to measure both the input voltage and the voltage across the resistor. But in my case, I reproduced the same setup in a simulation using the resistance to be equal to 100 ohms, the inductance to be equal to 0.1 Henry, and the capacitance to be equal to 10 microfarads. The function generator was modeled by a sinusoidal AC source with adjustable frequency and about 5 volts of amplitude. First, I built the RLC series circuit in a simulator and checked that everything was connected in one loop. Then I varied the frequency of the AC source from about 100 Hz up to 10 kHz using smaller steps around the expected resonance region, roughly around 150 and 200 Hz. For each frequency, I measured the voltage across the resistor using the scope. Since the resistor is 100 ohms, I calculated the current amplitude using Ohm's law. On the scope, I also measured the phase difference between the source voltage and the resistor voltage. This gave me the phase of the current as a function of frequency. All these values were recorded in a table. After collecting the data, I plotted current amplitude versus frequency to obtain the resonance curve. From this curve, I identified the maximum current, which occurred at about 160 Hz. So my experimental resonance frequency was 160 Hz. The two half power points where the current dropped to the maximum value of the current divided by square root of 2. These were around 160 Hz and 260 Hz, which I called F1 and F2 respectively. Using these, I calculated the bandwidth by subtracting F2 from F1, and then the quality factor by dividing the experimental resonance frequency by the bandwidth. So I compared this with the theoretical value of the quality factor, which is also about 1. So the theory and the experiment agree very well. Finally, a few words about errors and limitations. Even in a simulation, there are reading errors. I had to visually estimate amplitudes and phase shifts from the oscilloscope display, which introduces uncertainty. The frequency step size is another source of error. I only used discrete frequencies, so the true maximum might lie between two of my data points, slightly affecting the measured F0, F1, and F2. And in a real lab, there would be additional errors, component tolerances for R, L, and C, calibration errors in the function generator and oscilloscope. And despite these, the small difference between theoretical and experimental values for F0 and Q shows that model works very well and nicely demonstrates resonance in a series RLC circuit.